Say we have a signal x of n of arbitrary length, and let's say that its discrete time Fourier transform is equal to x of e to the j omega, which is the summation from n equals minus infinity to infinity x of n times e to the minus j omega n. Let's say that we sample this. So we let omega equals 2 pi over n k for k equals 0, 1, 2, up to n minus 1. So this means that our sampling period is 2 pi over n in the omega domain. So we had this x of e to the j omega, where omega was a continuous variable between 0 and 2 pi, and we sampled it at the points 2 pi over n, 4 pi over n, till 2 pi. And the sampled DTFT is equal to x of e to the 2 pi over n k, or we could call this x of k. This is summation of x of n times e to the minus j 2 pi over n k n. So we obtain this when we sample the x of e to the j omega. The question is, can we reconstruct x of n from the samples of x of e to the j omega? So let's try to compute this. Let's say that the reconstructed signal is f of m, and it's the summation of this samples times e to the j 2 pi over n k m, and these are the basis functions from k equals 0 to n minus 1. So let's put the x of k formula here into its place. Now let's exchange the places of the two summations. Let's put x of n outside, as it doesn't depend on k. And these are the remaining terms. We have m minus n. So let's evaluate this summation. This is equal to 1 minus e to the j 2 pi over n m minus n times n over 1 minus e to the j 2 pi over n k m minus n. So here the n's cancel out, and we can see that since m minus n is an integer, this is equal to 1. And this is not 1, except for m minus n equals 0. We will consider that situation separately. So this is 0. However, if m minus n is 0, or if m minus n mod n is 0, then e to the j 2 pi over n k m minus n is equal to 1 for all k. Therefore, that summation over there So this summation, if this is the case, this summation is equal to n, since we are summing up n terms. So here we can simply write, instead of this summation, we can write n times delta function n minus n. And this delta is periodic with n because of this modulo n. So, okay, we have this. So now each term in this summation is 0 except for n equals m or m plus an integer multiple of n, where r is an integer. So we can say that, remember, this is the reconstructed signal f of m. This is equal to x of m plus, we had this n multiple, let's not forget that, x of m plus n. We also have x of m minus n plus x of m plus 2n, x of m minus 2n, dot dot dot. So we can express this f of m as n times the summation, where r is an integer going from minus infinity to infinity, x of m plus nr. So we have this. If the length of x of n is less than or equal to n, then we can say that f of m over n will be exactly equal to the periodic extension of x of m by n. So in this case, we can actually reconstruct x of n from the samples of x of e to the j omega. However, if the length of x of n is greater than n, then we will have this formula over here, like the reconstructed signal will be a summation of the shifted copies, as you can see. And these shifted copies will overlap. So we will have aliasing. Actually, this is very similar to the time domain sampling case. Remember that when we sample in time domain, like if we sample the signal x of t with sampling period t, in that case, to recover the signal, to be able to recover the signal from its samples, we must have that the bandwidth of the signal must be less than 2 pi over the sampling period. This is a time domain sampling case. So for the frequency domain sampling case that we looked over here, the length of x of n must be less than n, which is equal to 2 pi over the sampling period. So we can see that this is very similar to the time domain case. Also note that if the signal length is m and my sampling period is 2 pi over n in the omega domain, then we showed that n must be greater than or equal to m, because we are essentially using n basis functions, and for a length m signal we need at least m basis functions. So this is expected.